Okay, today we will be continuing to one of the other ionizing radiation type of nuclear imaging technique, which is related to positrons. Namely, we will go through positron emission tomography system. But first of all, we have to go through the positron concept very briefly. This is actually a nuclear imaging or nuclear science concept. This is one of the subatomic particles produced from a nuclear reaction. The details of this physics and nuclear phenomenon is not our concern, but the outcome and resultant gamma ray is very important for us for the imaging purposes. First of all, what's a positron? Positron is positive electron, actually. Physics people call two subatomic particles as beta particles, and they are divided into two sections. Beta particle has two kinds. Beta minus is related to a negative charged beta particle. Beta plus is mainly a positive charged beta particle. We already know the beta minus particle. Beta minus particle is our general electron. So a charge which is electron charge, which is 1.6 times 10 to the minus 19 coulomb particle called electron can also be called as beta minus particle in physics. There's an analog particle which can also exist in nature, but it's very unstable. That's beta plus particle. Beta plus means the same charge, but the charge sign is positive, is another kind of particle called positron. Positrons, when they are formed, are very unstable because as soon as they are available and start traveling, it can attract nearby electron instantly. So they combine, for example, in this image, okay, this atom produces positron with a nuclear reaction that gamma ray having larger than 1.02 mega electron volts. That's very critical value. I'll tell you the reason why. Photon interacts with the nucleus and divides a kind of neutral particle into two parts with the same mass. Okay, one is electron, the other one is positron. When positron is available, as soon as it travels, it approaches to a nearby electron in another atom. So this distance is very short. So you can think of as soon as it's formed, it combines with an electron. This is called annihilation. Okay, annihilation means the event that they disappear. Okay, actually their mass disappear, but their energy is formed. So mass is here, is converted to energy. That energy is represented by two oppositely traveling photons. Each has 0.511 mega electron volts or 511 kilo electron volts. Okay, so that's the trick about positron. Some reaction forms a gamma ray, and this energy is transferred to divide an atomic particle into two parts. The positron annihilates with another electron, maybe, or its counterpart electron, who doesn't know. So a special two twin ray photons are formed. Okay, this is called annihilation. That's another important technical term. So positron imaging is done in creating positrons in an organ, because in that organ, those positrons create those rays, okay? So they are used for imaging. Of course, okay, this is also called a gamma radiation because that's a special energy gamma rays, two twin rays, okay? And the attenuation mechanism is the same as X-ray. The only difference is the energy of the photons are different. They obey the same rule of exponential decrease in the ray intensity. Intensity is defined as, you know, number of photons with that energy on a particular unit area. And mass attenuation coefficient, absorbance coefficient, and are all the same concepts like X-ray, okay? The most important ones as attenuator in this positron emission tomography energy levels are the, let's say, water, okay, because that represents the mean of all tissues. Sodium iodide, because that's used for detector scintillation crystal, okay? So scintillation means that crystal or that structure, chemical structure, receives gamma rays having 511 kiloelectron volts, and they are transformed to visible light, tens, thousands of visible light photons to burn the film or to be detected, okay? And lead, as you know, is a very high X-ray or gamma ray absorber. Half-wavelength thickness is very thin and used for limiting or confining the X-rays or gamma rays not to harm some other places. So that's a typical, again, everything's measured. There's no analytical mathematical expression. So mass attenuation coefficients, etc., are measured experimentally. This is a nuclear event, different than X-ray, okay? There's no tube. So there's some material which is decaying with respect to time. Decay means its nuclei, atomic nuclei, are transformed to other kinds of nuclei as time passes, okay? So any substance is called radioactive in this concept. Radioactive materials are used. Usually they are called pharmaceuticals, radiopharmaceuticals. That means pharmacological molecule has some kind of radioactive element bound to it, and that element is emitting gamma rays or producing positrons as the time passes. So decay, the unit of decay is 1 Curie. If 1 nucleus decays per second, usually that's a very low quantity. A higher nuclear medicine aspect, a higher quantity is called becquerel. It's about 3.7 or 37 billion decays per second. In medical applications, usually millicurie is used. So we have to go through another definition of half-time. Half-time means you have some substance and number of decays are that becquerels at specific time. After a half-life period, that decay drops to 1/2 of this value. That means the number of decays decrease by 1/2 in 1/2 time period, okay? So physical substances do have specific half-times depending on the molecule structure. They are given in tables and presented in these forms by nuclear specialists. Also, special to that medical imaging field, we do have biological half-time as well. Biological half-time means that the person takes that nuclear substance into the body. Okay, that's the first difference to other imaging modalities. You remember in other imaging modalities, we have energetic source outside the body, and that source sends rays to the body, and then they are detected at the film or digital detector outside the body. So body was between the source and detector. Here in nuclear medicine, the source is the body itself. The person intakes the biological or radiopharmaceutical substance. That substance accumulates in specific organ, and the doctors know these things before because they have been uh, pharmaceutically researched. Special for a special disease, for a special organ, receives that molecule and gathers that molecule goes to that organ specifically. And the aim is that because we want that organ sends ray to be imaged. Okay. So there's a kind of time curve. When the patient intakes the material, it takes some time to gather maximum concentration at the organ, and then slowly that foreign material, radiopharmaceutical material, is sent out of the body. So there's a kind of diminishing curve of that concentration in that specific organ. So that's called a biological half-time. The time required for the organ to increase double the concentration, double, or to decrease to half, usually in that case, to decrease to half is called biological half-time. So you give a concentration or radioactive material to the body with some decays per second, and biologically it starts gathering in that organ. After some peak time, peak value time, due to biological half time, the concentration in that organ decreases chemically. At the same time, the same material, pharmaceutical material, is producing decays per second different than the moment that's being injected or given to the body. So both of these time constants are active on the realistic final situation. So the doctors tell the person, the patient intakes that pharmaceutical either by injection or by swallowing or by breathing or some other methods, okay? And the doctor says that wait some time, 15 minutes or 30, depending on the examination, to catch the peak time of organ gathering. During that time, the substance also has some physical half time. So on the patient, we have two different half times called material half time and biological half time acting together to yield effective half time of the substance for imaging. Okay, so this is the definition of an effective half time. So after these first definitions, let's focus on the instrumentation. What kind of systems are used to perform nuclear imaging? By the way, nuclear imaging is a very special technique. It gives information about the function of the organ, not anatomic boundaries, but intakes and molecular processing, biochemical activities are mostly observed in this imaging systems, okay? The patient is given very low quantity of radioactive material since it's dangerous. Low radioactive quantity means less number of gamma rays, which means very bad SNR, very bad signal to noise ratio. So the patient is under the detectors or cameras for a long time for increased number of data collection to increase SNR by the square root of number of experiments, okay? So the blurring is also high because the photons are very energetic and scintillation crystals are very thick to capture all photons, which includes more blur. So although the advantage of these systems are their physiological parameter showing systems, which are unique for all imaging systems, they have disadvantage of poor SNR and radioactive materials, handling, patient care, etc. So instruments, first of all, physical instruments are needed. Somebody has to carry some radioactive material to the hospital, prepare appropriate dose for the patients, etc. So there's a kind of special place for radiopharmaceutical preparation for each patient. Usually in the mornings, hospitals receive radioactive material, and they cannot be stored in refrigerators or whatever. They should be utilized during the day long, and that's over, because their half time is also determined to be low in order not to affect patient and surrounding people. Okay, so they have to be very fresh. There's a kind of nuclear material preparation room or chamber or division in a department. Patient lies on a table, and there are detectors around the patient because there's no source, no gamma ray radiation inside from the instrument. The only gamma ray source is the patient itself. So in that nuclear imaging department, people running around are actually sources of gamma ray. They are emitting rays, so they have to be wait in a special room, shielded with lead or other stuff, not to harm other divisions of the hospital. The most important part of these instrumentation systems are their detectors and their computers. Detectors. Detector means we have to capture 511 kiloelectron volt photons and capture efficiently. That means you have to capture all photons, but you have to be careful not to capture scattered photons. You have to be specifically capture 511 keV oppositely traveling photons. There are some so-called coincidence detectors. Assume this is the patient and this point is active, then the detectors are mirrored or 180 degrees apart. So any action to gamma ray coming from the patient in a linear way, if you capture at the same time or very close times, then those are valuable captures. But if one of them is scattered, you don't want to capture it. So detectors are really important in that sense. The other thing is detectors should be very sensitive because we are working with low number of gamma rays. So some kind of collimators, good collimators, and photomultiplier tubes and gamma ray amplifiers, etc., should be utilized more in those systems. Also, we said that scattered photons should be eliminated because they give wrong information. They mean if after they scatter, they are coming from a wrong direction. So that's the reason they should not be shown on the image. There are a couple of types of detectors. This is like solid state detector. That's a semiconductor material. If radiation is incident on the junction layer, charge couple pairs or electron hole charge pairs are formed if they absorb the energy. So the electronic circuitry current increases. That's proportional to the number of photons. And also vacuum or tube kind of detectors utilizes the same principle. The ray ionizes ions, electrons and ions, and they increase the current. That current is measured, and this current is proportional to the number of rays. Collimator is also very important because it has to focus on some special place. Since the SNR is low, you have to get only very useful 180 degree opposite direction gamma rays. There can be a couple of geometries of collimators. This can be focused to investigate activities in small organs like thyroid glands. These collimators are from a larger region, skeletal or abdominal or other similar. They collimate parallel beams, not focused to specific place. And this is the cross section of one detector. That detector is usually very heavy due to lead and metal structures and lots of instrumentation in it. And each little circuit is a cross section looking from top or bottom. Each little square corresponds to an area of a photomultiplier tube. So in that square, if a gamma ray hits, then due to sodium iodide crystal or scintillation crystal, that high energy gamma ray produces visible light photons, and the number of photons create on the phosphor screen create electric current, or in a charge coupled device, electric voltage. So voltage and current or current are proportional to the number of visible lights coming into the area. Usually, the number of since the blurring is high, one gamma ray produces a very large diameter of visible light photons due to blurring. So multiple tubes receive varying number of photons. By measuring the number of photons or intensities under each photomultiplier tube, corresponding, if you get the weight of the position, if you consider the weight of the number of photons, you can very accurately calculate the exact position of the gamma ray hitting the scintillation crystal. Usually a couple of centimeters is the diameter of each photomultiplier tube, and the resolution of the nuclear imaging camera or gamma camera, also called with Anger camera, the resolution of the positioning of a nuclear imaging experiment is up 5 to 10 millimeters or so, okay? So these can be calculated from the multiple receive of gamma ray photomultiplier tubes and processing with computer methods. So one of the most important parts in a nuclear imaging system is the gamma camera, also called Anger camera. Anger is the last name of the engineer that had developed this camera. From this camera, we have XY two-dimensional location information, as well as so-called Z-pulse signal. Z-pulse is related to the intensity. How much part of, or how many visible light photons are incident on the tube. So that's an explanation of the Z-pulse. So we receive 3 types of information, 2 for the location and 3 for the intensity. When the patient has pharmaceutical in the body, these chemicals circulate in the blood and gather in the specific organ. So what's happening just before the imaging? Okay, so assume this is the organ, and the person has most radiopharmaceuticals in that organ, but many other pharmaceuticals due to bloodstream around the body. Okay, but comparatively or compared to the organ, the concentration is really low. Now this detector receives that violet colored rays because those rays are informative, but we cannot catch them. So that's another reason of bad SNR for this system. This is 3-dimensionally emitting rays, but only a part of solid angle rays are collected, okay? So, for example, the parts receiving more rays do have greater intensity in the reception. less rays, due to their electronics, voltage and current intensity is lower. So this is called the Z-pulse. Okay? Z-pulse gives an idea about the intensity of the incoming photons. If you increase the number of photons, your intensity is higher. So there's a method of Z-pulse detection, and that detection also has valuable information for the people or doctor or imaging purposes. So this is another principal view of the Anger camera. This is a big cylinder and lots of electronics from each photomultiplier tube, and each amplifier is a logarithmic and amplifier stage electronics identical. And you see, look, this is the organ, and assume these are valuable lights, and this PET, positive emission, is a scattered ray. This one is scattered, this one is scattered, these are not scattered. So the information here is wrong because it assumes that it receives the same thing like here, but actually not. So we have to check the Z-pulse, check the energy of the photon. If the energy is quite low, that means it's scattered a lot and it does not contain valuable information, so it should be regarded. So this energy, low energy pulse, should be disregarded. Okay, so that's the importance of Z. So there's a circuit or system or software called pulse height analyzer. Pulse height is related to intensity, and if you analyze the pulse height, only the intensities above a threshold would be valuable for imaging. They are sent to imaging screen, others are not. So I told the most important part and the detector side and its electronics in the previous slides. Then how can we objectively measure its quality, imaging quality? You remember those figures? They are black and white stripes, and modulation transfer function of this imaging system also can be performed, except these are not on paper with black and white paint. Rather, this is a volumetric field box full of radioactive liquid, but the black regions are some solid material which that radioactive material cannot penetrate. So these are not active regions, radioactive regions, but the rest radioactive. So their image is like this. And the method forming the MTF is the same as your camera. Okay. So that's about it. We will be ending the 40-minute allowed time for the slides. We will continue to start at 16 hours. But you may ask,